Hello, here we are back at the whiteboard, and I wanted to take a little bit of time here to explain some basics that people probably need to understand the larger video, and to begin a discussion on what some people believe are root causes of the crash and can't possibly be the root cause. And I'm going to explain that as we go along here. But the first thing that I wanted to hit on here is that many people, almost all, think of aircraft flying statically. We draw pictures that have vectors and the wind and this, and the aircraft, but it's sitting still. And that's not how aircraft actually fly, as I put up here on the board. Flight is never steady state. We analyze it as steady state because that makes the math a far sight easier. It keeps us away from the partial differential equations, which you have to be a very unique person to like to work with those. But when we analyze these crashes, we have to stop and think that the aircraft is moving, and that is changing the situation every moment the flight progresses. We can't just draw one picture and say, here's the forces, and that's why it crashed. It can be a part of the answer, but it's never the whole solution. We have to look at how the aircraft was flying dynamically. Now, in this case, we know that the pilot reported via radio that he was having problems trimming the aircraft. And considering he was on final approach to land, we have to assume that has to do relative to the speed that he's flying and the speed that he'd like to be flying at, and whether or not he has enough control authority to achieve that configuration of flight, a certain speed at a certain altitude. He must have landed at a certain speed, and he's having a hard time trimming the aircraft. The only controls he has are the flaps and the elevons. So he can either put flaps down or up, and he can put elevons up and down. And those forces have to balance out such that he's at a trim speed that he wants to fly at. It's that simple. So if something goes wrong and he can't achieve that trim speed, well, there's a variety of things that could happen. And I wanted to take a quick look at what some people talk about. People talk about, oh, the flap was too big. And of course, they're not specific. They don't say it was too much area, it was too much span, it was too much guard. No, it's just the flap was too big and it overpowered the elevons. Well, we know for a fact that the Flair could fly with the flap down because there's a lot of pictures of it. I'll put one up here. They had 50 flight hours on it, and they had flown with the flap down. So there apparently was enough elevator command to counteract at least that much flap. How much flap that is, we don't know. I can look at the picture and say, oh, maybe 10 degrees, maybe 15, something like that. Did they ever go more flap? I don't know. I don't have any pictures that clearly show more flap down and elevons way up. Where would they run out of elevator command? I don't know. I'd have to go do a bunch more analysis to find that out. And I'm probably not going to do that analysis because I believe I already found the root cause. And it's not the fact that the flap overpowered the elevons. That could have been a contributing factor, but probably not the root cause. And that's because of this. As you put the flap down, you get a nose down pitching moment on this thing, and the glider wants to descend faster like this. So you pull in up elevator. You pull that stick back, pull the elevators up, and get back to a trim speed. Now your trim speed with the flap down and elevons up is different than what it is when you're completely clean configuration. So you put the flaps down a notch. Whether they have notches or not, I don't know, but you go for a setting. You put it down 10 degrees, and the glider starts to descend. And eventually, well, oh, that's too fast. I pull in up elevator, but I need more flap to slow up the land. So you put in more flap, and now you pull in more up elevator, right? Until you run out of elevator. And then you're at some flap setting that's causing this rapid descent rate, and you got full up elevator in, and you can't get the glider slowed up. Well, that's this kind of trajectory right here. It's an arcing trajectory that heads on down to the ground. And it takes time for that to happen. This is like an incremental thing. I don't think anybody would come in and just dump full flap and find out they don't have enough elevator command. Might have happened that way, but then there's another root cause to the accident, and it's not the fact that he ran out of elevator command. So he'd be on this type of trajectory. You're putting the flap down, and usually when you're on approach, you put it down in notches. You add a little more flap, add a little more flap. And he's a very experienced pilot. He would know to do that. Well, you got plenty of time here to say, oh, this is not working. I put on 2 notches of flap and I don't have any more elevator command. And, I've flown, not me personally, but that pilot had to be thinking, he's not even thinking. He's flying by feel, too high of a descent rate. He's run out of elevator. He's going to pull the flap back up. He's going to pull the flaps up. He just put on a notch. He can't get back to trim speed. He pulls the flaps up. And that could have been part of what he was talking about. I can't get the aircraft trimmed. He might have been through this cycle a couple of times. I'm putting the flap down, but I'm running out of elevator. So he pulls the flaps back up and tries a different configuration. And he can't get it trimmed. But he's got plenty of time to make adjustments for that. Now, I know from recent input from one of my viewers that the correct translation from the original German accident report says that the glider impacted perpendicular to the ground. That means he was going straight down like this one over here. Let's see if we got it on here. Do I have to move the camera a little? There it is. Sorry about that. This is off the board. This is what actually happened. He went straight in like this. Well, if you're at 50 meters and you went into free fall, that gives you about 3 seconds before you hit the ground. Now, he wouldn't go absolutely free fall. There's a little bit of drag from the glider and so forth. So maybe he's got 4 seconds, 3.5 seconds, somewhere in there. It's fast. It's really, really fast. This is an abrupt change that had to occur here. It could have been where it was a geometric progression. It's just getting worse and worse and worse. You're going into a dive like this, and down you go. That could have happened. That's going to take longer than 3 seconds. Is it enough time to respond? I would have to say yes, because I've had problems on my glider that I've responded to in less than a second. I've had some that are more than that, but I've had ones that, let's see, my most recent one where I ran out of down elevator and the climb that's occurring, I was about 3 seconds into it, and I'd already tried a couple of different stick positions that were extreme, decided I didn't have enough down elevator, and I got off a toe. So more than 3 seconds is enough time to make corrections for whatever you just did that's wrong or causing a problem. And in this case, it was probably the flaps. So if it's this type of trajectory, he's got plenty of time to try something else. If it's this type of geometric progression, in a panic move, he could just yank the flaps up and he'd zip right back out of that. It's this one over here that he doesn't have time to respond to, where you're flying along and the nose drops and you plummet out of the sky. And that's what's been reported. And the people that witnessed this accident were mostly pilots. So when they say the nose suddenly dropped and he fell out of the sky and he hit perpendicular, and it came in perpendicular to the ground, it's probably accurate. So this is something that happens so fast that it shocks the pilot. You panic for a second, and that's the only second that you had to do something about it. And the next thing you know, it's all over. So, and that's what has always bothered me about this diagram. This diagram was in that initial accident report. Many people have mentioned this. Oh, it is the separated flow off of the elevon, lost pitch control, and went in. And this diagram has always bothered me for a variety of reasons, but the main reason is, how did it get into this position? How is it that the aircraft all of a sudden went nose down like this? Or how did he fly it into this position? There's no explanation in any of these reports as to how the aircraft got into this configuration. If it did get into this configuration and the flow separated, well, yeah, then the conclusions are correct. But the conclusions are not correct if you don't explain to me how you got into this position. So that tells me, because there's no explanation about how the aircraft got into this configuration, you haven't found the root cause yet. You may have found a secondary cause that made it worse. You might have found a tertiary cause, but you haven't got me to the root cause of what started the whole thing. You have to get back to explain to how did the nose get down in this position? Really dumb pilot committing, maybe somebody committing suicide, shoves the stick forward. Well, that still takes time. You get a geometric arc like this. You don't just, the nose drops and you fall out of the sky. And this doesn't explain that either. It's not like you're flying along straight and level and all of a sudden the flow separates and down you go. It's not like you're flying along and I'm putting down flat but running out of elevator, going down, and all of a sudden the flow separates and then I plummet. No, because you're not a stupid pilot. You pull the flap back up. I've run out of elevator control. When I put the flap down, the flap's coming back up so I can keep flying the thing. No, this was sudden. This was a sudden accident that surprised the pilot. And he didn't have time to respond. When we look at these static drawings, we have to remember that the aircraft flight was dynamic. And then we have to find out, how do you end up like this? Okay. So that said, I wanted to talk a little bit about some basic aerodynamic parameters and ways of looking at flight that we use in the engineering world. I think you understand about these trajectories that he could have been on, and verbal reports said it was this type of trajectory over here that was, he just dropped out of the sky, impacted vertically. So let me, and the big question here is, where's the relative wind? Because the relative wind is everything. And if you stop for a moment and you think about all the aircraft that you've seen doing aerobatics and so forth, it's like, well, gosh, he's going vertical, but he hasn't fallen out of the sky. How is that? Well, you can be vertical and still have positive lift. It's very possible. What you need to know about aerodynamics and lift to understand all of these other issues I'm discussing is a couple of basic things. We have a chord line. Do I have a straight edge here? I don't have a straight edge. Now you're going to watch me try to draw a straight line. Artists can do this so well, and I cannot. That's not too bad. I got a little wavy at the end. Okay, the chord line, C, is the maximum distance from the nose of the airfoil to the trailing edge. That is the chord of the airfoil. And the relative wind is this. And this angle here, alpha, is the angle of attack. Angle of attack is always the angle between the relative wind oops, let's make that move. Angle of attack is between the relative wind and the chord line. This is important to remember. I'm going to be talking about it later. Airfoils stall at a specific angle of attack, not at a speed. We talk about stall speeds, but that's just to make it easy on the pilots because they have an instrument that has speed, airspeed, and they know not to go below a certain speed because at that speed, this airfoil is going to be at a high enough angle to stall. We don't want to have that happen. But in reality, airspeed has very little to do with stall. Angle of attack is what causes the stall. You get a high enough angle of attack, and the flow that's going up and over this airfoil can't make this steep of a curve. It's trying to go up and over the hump, and you have a drop in pressure here, and you're trying to gain pressure back here, and it can't stay attached. You exceed the Stratford pressure recovery criteria, and the boundary layer starts to reverse, and then you get turbulent flow back here, and this goes off this way, and this creeps forward on the airfoil until the whole thing is stalled, or stalled enough that you fall out of the sky, or at least you begin a rapid descent. Now, a lot of airfoils have a very gentle stall on them, and as you approach stall, you get a burble on the wing. When this first starts to separate back here, and the aircraft will start going like this, and you know to put the stick or yoke back forward and get that angle of attack down and get your speed back so that you're flying. Now, all of this configuration for stall can happen at any angle relative to the ground. You could be headed down at a 45-degree angle and stall the wing. Depends on the velocity vectors involved. Or you could be pointed nose up and not stall. You can be pointed way up in the sky like this and not stall, so long as the relative wind has not exceeded your stall angle of attack. So if you have enough speed, if you're coming along here really fast and you start doing a pull-up like this, and I got enough speed to carry me up, I'm moving forward. I am dynamic. I'm an aircraft that's moving forward. So that means the relative wind is not here where it was before. It doesn't stay there when I pull up like this. This doesn't happen. No, the relative wind goes with me. And eventually, as my speed bleeds off, that angle gets steeper and steeper and steeper until I stall. And then you go back down. In fact, in the gliding world, we practice these, and they're called accelerated stalls. We have stalls that we practice where we go along and we just like slow it up, going slower, slower, burble, 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 put the nose back down, get back to flying. That's the start of a stall. We have other stalls that we practice where maybe we put down the nose a little bit, pick up some speed, and do a big pull up like this, and wait and wait and wait until that relative wind is at the appropriate angle for a stall, and then the aircraft will go through a complete accelerated stall, which is generally that you get the separation occurs all at once. You might have a little bit back here, but it goes boom, and it all separates, and you lose the majority of your lift. And that's when the glider pitches down rapidly, depending on how accelerated you were coming into it and how vertical you got, pitches down rapidly. And then you put the stick forward and begin your recovery. You let speed pick back up so that, and as so the aircraft pitches nose down, but this is a dynamic event. It happens quickly, so the relative wind is still somewhere over here, and as you pick up speed, the relative angle of attack comes back as you pick up speed. That's why when you do accelerated stalls and it breaks, it finally breaks into the stall and the nose drops, well, you can't just pull back on the stick right away. You're still stalled. You've got to wait until you pick up enough velocity to make that relative wind vector move around to where you're at a positive angle of attack that is below the stall angle of attack. And then you can pull back up on the elevator and slow the aircraft up. If you pull back immediately, you just go mushing through the sky and have repeated stalls and all that other stuff. So, really important, relative wind is what we really need to know. Where is it? What's our angle of attack? And in that diagram, they don't tell us. So, but knowing that there was a sharp nose down and a perpendicular descent to the ground tells us a lot. That tells me that something took all the lift away from that aircraft rapidly, much like doing an accelerated stall in a glider, where the flow separates, you lose all your lift, and down you go. And then the nose pitches down. And then that type of dynamic, the dynamic where you're flying along and magically your lift disappears, nose drops, you head straight down, and that's when you get this. So it's the events that occurred prior to getting into this configuration that have something to do with the root cause of this accident. There was something that caused this aircraft to lose lift and allow the nose to drop suddenly. That was actually at the root cause. And that's what I'm going to show you in the computational fluid dynamic data that we're going to review in just a couple of moments here. So remember, angle of attack has to do with the relative wind and not with the configuration of the aircraft relative to the ground. And we're going to hunt around for a solution that shows a drastic loss of lift almost instantaneously. Hey, welcome to the wonderful world of computational fluid dynamics. I am here in my den running Xfoil 5, and I'm running version 6.61. This program is available online for free, and I've put a link to where you can download it in the description of this video. So what you're looking at here on the screen is the Flair 30 airfoil as best I know it. I took pictures from various publications, enlarged them about 400% up to the size of the mean aerodynamic chord for the Flair, and digitized. And that's what you see here. And then I made some minor manual adjustments up on the front end here to smooth out the nose here. But as we'll see in the long run, the exact shape of the airfoil just doesn't even factor into what caused the crash. So whether it's this airfoil or a Clark Y or anything else, they would have had the same problem. But we're going to look at their airfoil as best we know it and compare it to some airfoils that are doing the same type of work. And we're going to see some fascinating factors. So there is the Flair 30 airfoil. And as we go forward here, I'm just going to substitute Flair for the Flair 30. Even though there was a Flair glider that came before the Flair 30, I'm just going to refer to this one as the Flair. So I have a bunch of configurations of this airfoil set up here, different flap configurations, and some comparison airfoils. And I'm going to turn on one here that is probably the better comparison, if I can get the right one. There it is. The yellow lines here are the Swift airfoil, the original Swift, not the current Swift 3 that's out. I don't know what airfoil they use on that. We'll see. These airfoils share a lot of characteristics. Lower surface, pretty much the same. Front end, highly similar. Flair's got a rounder leading edge that can help soften the stall characteristics sometimes. And its maximum thickness point is further aft. They trip the flow later on. The Swift trips the flow up here about 30%. And they both are using some form of Stratford pressure recovery technique. And that's to generate high lift at relatively low drag. And when you do that, you get these interesting shapes aft of the maximum thickness point where you're recovering the pressure as fast as possible without tripping it into separation. Although we see that the aggressive recovery of pressure on the Flair is not nearly as strong as it is on the Swift. Now I've gone out and tufted a Swift airfoil and it performs exactly as predicted. I haven't been able to find any pictures of the Flair being tufted, so we don't know anything about what the flow conditions might have been on this airfoil, whether it be separated, attached, whether they could have done a stronger pressure recovery. I don't know. I can probably accurately surmise that they moved the maximum thickness point aft because they're trying to delay the onset of turbulent boundary layer to keep the drag low. That would be a normal course of design events. So Swift, Flair 30 share some characteristics. They were probably both generated the same, using the same methodology, maybe even the same code. These are airfoils that are generated by, you set up a code saying, here's one I want. I want this kind of CL, I want this drag, I want this kind of pressure recovery, yada, yada. You put in those parameters and it draws the airfoil for you. So this airfoil will perform and deliver those characteristics. I know that was used for the Swift. I would suspect it was used for the Flair. It's very popular at the time to design airfoils that way. Okay, now on to a completely different airfoil. I want to turn these, I'm going to turn off the Swift and turn on the airfoil that's on my wing. If I can get it to actually stay on. There we go. Now, the brown line. That's the NACA 23012. I use it outboard of my winglets, and inboard I use the 23015, a little bit thicker. I chose this airfoil because there's a vast amount of data available for it. It was designed back in late 30s, early 40s, and it probably has more wind tunnel time on it than just about any other airfoil. It's just been studied up and down and left and right, and its characteristics are well known, and I can easily run this airfoil in this code and generate data that looks just like wind tunnel data. So I know that I can use the code safely to predict how my wing is going to behave. That's a good thing. Now, the biggest difference that you see between these two airfoils, and I'll turn off the Flair one, notice on the 23O series, they have this little flat area up front here, flatter area. And what that does is that bumps up the mean camber line here. It causes it to be quite steep up front, and then comes as you get back to about here, the mean camber line starts to pull back down, and eventually it reflexes out to the trailing edge. What that does is it front loads the airfoil. It puts most of the lift way up front here on the airfoil, especially as you get up to higher angle of attack. It's just this first, 5 or 10% of the airfoil that's generating a big portion of the lift. And that can be beneficial because that helps counteract the nose down pitching moment. And by reducing the nose down pitching moment by putting the lift way up front, you reduce the amount of downforce that has to be carried by the tail. And that means that you can make the tail smaller. Or in our case with flying wings, you can make the elevons smaller, and they don't have to be swept aft as far, or you don't have to put reflex in the wing. This is a very neutral pitching moment curve all on its own. So with my design, I don't have to carry as much downforce out at the wingtips to counteract the nose down pitching moment of my airfoil. And hopefully in the long run, even though this is a little bit draggier than the Swift airfoil, my overall configuration might be a little bit better at certain speeds and certain angles of attack. And that would only be borne out in extensive flight testing. And so there you go. That's the 3 airfoils that we're going to look at in this analysis. So now this program allows one to analyze just about any shape and give you standard aerodynamic parameters. And that's down here in the direct analysis package. And here we're looking at the Flair 30 airfoil in its baseline configuration. That's without any flap deflection. In the upper right, and all of these graphs will be the same. Upper right, we have coefficient of lift versus angle of attack. Upper left, we have the CL over CD. No, the glide ratio is not 110. This is CL over CD. In reality, we would expect something, a theoretical maximum L over D for the Flair to be somewhere around 30, 25 to 30. And here's the pitching moment curve. The pitching moment curve for the Flair airfoil is minus 0.045 approximately. 0.047, somewhere around in there. Actually, I could put my cursor on here. At zero angle of attack, its nose down pitching moment is 0.047. I guess pretty close by eyeball. And then as the angle of attack goes up, the nose down pitching moment gets worse. And then this is typical of airfoils. It comes back up and swings back up and then back down again. And so it's not horrible. It does have a nice flat drag bucket here, all the way. It does pretty good all the way up to a CL of 1.2. This is where on the lower right graph. And then once you get to a CL of about 1.2, the drag starts to run up, and then once you get up here into the stall angle of attack, then it's just all drag and no more lift. So that stall angle of attack occurs right about here, somewhere around 9 or 10 degrees angle of attack. And when I first saw this, I thought, well, that's not very good. I know my airfoil goes to 16 degrees, way over here. I don't stall till I get way over here. And at first I didn't know where the Swift was, but I now know that where the Swift lies, and it's even better than this one. So kind of a wimpy stall angle of attack, and I suspect that's because of how they positioned the transition point being well aft and how they did the pressure recovery. This airfoil is not performing efficiently. It crosses the zero lift line somewhere over here at a negative angle of attack, which for a flying wing is not necessarily a good thing. Generally, that means you need more washout to counteract that nose down pitching moment. But we know that the Flair had only 5 degrees of washout in the wing. That was probably just barely enough to fly. It really should have had 10 degrees. It would probably flown reasonably well at 8. 10 would have been better. The reason they kept the washout low is to reduce the drag and get better performance. But they created a wing that had handling issues to some extent. Okay, so that's the Flair 30 airfoil. Let me pull up the Swift, an airfoil that does this job extremely well and was designed by multiple Stanford PhDs in aero engineering. grinding on that program over and over and over until they had something that they thought was really good stuff. And it is. And for the day, oh, fabulous. So let's go right back to CL versus alpha. Here we see it has almost the same slope as the Flair, but it passes through the zero lift at pretty much zero angle of attack, which is what you want for a flying wing. It peaks out here at about 157, 1.57 CL, and the angle of attack is just shy of 12 degrees, 11.7 degrees. And we see it has a fairly sharp stall here, but that's for the airfoil. All of this analysis is for 2D airfoil. It's as though the wing is infinitely long. It's the maximum performance that you'll get out of the airfoil. So it has a fairly sharp stall, drops off, then plateaus off. Typical stall curve, other than the fact that it's a little bit sharp. But we don't really worry about that because an airfoil is not a wing. I'll say that again so you always remember it. An airfoil is not a wing. You're looking at airfoil data, you're not looking at a wing. And by combination of washout and other factors, you can soften this stall here. And we see it has a fabulous CL over CD. Blows the doors off of the Flair 30, which is over here. They're way up over here. And they can pull that lift to drag ratio at a pretty high angle of attack. It occurs just before, maximum L over D is just before stall. And down here is really impressive, the drag bucket. Flat drag here over the full spectrum of angles of attack, even slightly negative. And it's all the same drag, same drag, same drag, same drag, same drag as you go up in CL. So you're gaining lift, but the drag's not going up, which means that your CL, that your L over D is improving. As you go closer to stall, you're getting a better L over D, which is great because as you go slower and slower, you're probably heading towards thermaling or light lift conditions, and you want more L over D, and that's exactly what this airfoil does. And it does it extremely well, and it gets up to the corner here, and then you lose that effect rather quickly, and that's kind of mirrored by the sharp stall that's here. And then the drag goes up rapidly, drops off. The Flair does have the advantage of you can continue to try to pull more CL. You get a little bit more CL, and you just get a boatload more drag. And the Swift, you drop off. And we see that up here in the lift curve slopes. The Flair comes up here and kind of plateaus off and just goes wandering off like this. It has an indecipherable stall. As a pilot, you might feel that stall, you might not. On the Swift, you know you've stalled. You might not get a lot of burbling first, but it's going to drop its nose and go back to flying. The Flair is just going to flounder around, maybe in a stall, maybe not in a stall, with the drag going up and up and up. And then we go over and look at the pitching moment curves. Wow, what a difference. So the Swift was down here at minus 0.02, less than half of what the Flair is, although the airfoils look somewhat similar. Drastically different pitch moment curve, and it stays pretty flat all the way up to the stall angle of attack. In other words, the pitching moment of the glider, its tendency to go nose up or nose down, is not changing much as you go through different angles of attack, and that's very handy to have as a pilot. You're not chasing the pitch all over the place. It stays well behaved, and you can pull the nose up, and you don't have to worry about jockeying the controls around to try to trim the aircraft. And remember, we had reports from the Flair pilot that crashed. He was having difficulties trimming the aircraft as he slowed it up towards stall. And that its stall is down around 10 degrees. Let's look at 10 degrees over here, and we see that we have an inflection here. The pitching moment is changing. It's heading back up. It's got a little burble in it here. I don't know if that's real or not. And then it goes the other direction. So this can be maddening to a pilot to try to fly an aircraft through this. He might feel it, he might not, but if he's got a good stick hand, he might say, something's going weird with the pitch here. So there we go, a good airfoil and a mediocre airfoil. Now let's look at my airfoil and see if Raul did a halfway decent job of picking an airfoil for his glider. Well, wow, it sucks on L over D, at least for the wing section, okay? But upper left curves, we look at that and we say, oh, it won't pull as much L over D as the Swift or the Flair, but I have a wide spectrum of angles of attack where I have decent L over D. That can be an advantage when you're in cross-country competition, because somewhere in there you're going to have to fly fast. You're going to have to fly down here at low angles of attack and not have, and still maintain relatively good L over D. Now, the Swift is going to do a little bit better than me. And up here at the high end, well, because my stall, I'm looking at the upper right now, my stall is way out here at 16 degrees and it's a soft stall. So I can slow up and pull a higher L over D than the Swift. So when it comes time to thermal, I have a broader polar than the Swift. And in the aggregate, on a competition day, might be able to outclimb them and then get to the top of that thermal sooner and reconfigure for fast flight, pull the flap up and go fast and maybe win the day that way. So when you're in competition, it isn't just absolute L over D that wins the day. It is, in my mind, you win the day by having the broadest polar possible so that you can fly in the widest variety of conditions at, on average, good performance. In some cases you'll outrun them, some cases you'll outclimb them. Okay, now, one of the benefits of my airfoil is the soft stall. Now, I've flown this airfoil a lot on gliders such as the 233, the 134, the 232, and the 126, all Schweitzer aircraft that fly beautifully. And I like their stall characteristics. You get a very distinct burble that starts here. It warns you when it's about to stall. And that allows you to avoid the stall. You get the nose back down. You get the rumble, the rumble, and you get that nose back down before you go through a full stall. And for me, on a flying wing, that's very important because that helps you stay away from a spin. Flying wings are very prone to spinning, and the best way to avoid spinning is to avoid stalling. And the best way to avoid stalling is get the nose back down before you stall. And you need some kind of warning for that. And with this airfoil, that comes automatically built into the airfoil in this drop off in the lift curve slope and the early separation on the trailing edge of the wing. And you get both a physical and a auditory warning that you're about to stall. Now, my CM curve, pretty much like the Swift, and mine's only minus 0.01. I have the lowest pitching moment curve out of these three airfoils at 0. So that means I need either less washout in the wing, less reflex in the airfoil, or less up elevon to achieve pitch trim. And that holds pretty good until I get out here to about 10 degrees, and then it starts to go up kind of quickly. And if we look at my curve at 10 degrees, that's where it kind of starts to fall off here. The lift curve slope starts to fall off and arc over, and we get a change in the pitching moment curve. So as you approach, now this is the interesting, as you approach stall, as you slow it up and getting towards stall, the pitching moment curve changes to nose up instead of nose down. So that means you need less and less up elevon in order to achieve a higher angle of attack. And that's what I really like. Another one of the things I really like about the airfoil is that, because if you have to put in a lot of up elevator to pull that nose up, you're dumping lift and creating drag. And that's the last thing you want when you want to fly slow. I don't want to dump lift, I want more lift. And this allows me to do that because I don't have to deflect the elevon as much. The increment more elevon I have to put in to get an incremental change in the L over D is smaller than these other airfoils. It's easy to trim at a high angle of attack, and it's easy to avoid a full-on stall. But here's where I kind of lose the game a little. I'm doing almost the same as the Flair. I can do a higher angle of attack, so I can pull more L over D than the Flair, but in this range here, at the corner of the drag bucket, the Swift will outfly me. I have more drag. I can't pull as much L over D in this region as the Swift can. But overall, if you look at all the curves on the whole, when it comes to flying slow and flying fast, a broad speed range, I think I would win the day. That'll be proven out if I ever get my wing flying correctly. So there's the three basic airfoils and how they behave with no flaps, no elevons, and just running through an angle of attack. Now I should say I made all of these runs at a Reynolds number of 1 million. And that's because at normal cruise speed on these aircraft, that's about what the mean aerodynamic chord operates at, somewhere between 900 and a million on the Reynolds number. So I just made them all a million, and we're staying away from problematic areas like 750,000, 500,000. That's for another discussion later. And I set the transition point on each airfoil based on basically where the designer set it. The Swift I know I have correct at 30% because Steve Morris told me that's where they put it. On the Flair I guessed at about 40, 45%. Actually about 40% I think I put in because they're probably tripping it before they get to the hinge line. And on mine, NACA airfoils, they trip way up front. It's in the first 20% of chord. You trip to turbulent boundary layer, and that's really why you have this extra drag here, is because it's a fully turbulent boundary layer at this point, and it's most of the airfoil, so it's a little draggier. So there we go. And anything else I need to discuss here? No, I don't think so. So for going forward, I'm going to turn off my airfoil and the Swift. So here we are back at the baseline Flair airfoil. And I looked at this and I thought, well, yeah, it's kind of mediocre, but I don't see anything that would cause it to fall out of the sky. I see something that's a little spooky for pilots here. They don't know exactly when they've stalled, but there's other ways to deal with that. And once I had these data points in there, I was intensely curious as to what happens when you put the flap down. And I felt that a normal flap setting for takeoff or initial landing approach or takeoff would be about 20 degrees, anywhere from 15 to 20 degrees. I use about 20 degrees on my wing. Lots of aircraft use only 10 or 15 for takeoff. It varies, depends on the airfoil and the aircraft. So I set up a Flair airfoil with a flap set at, so that it's articulated at 45% of chord, that the flap itself is 45% of chord. The hinge line is actually at 55% of chord length, which means that 45% of the chord is dedicated to the flap. And I set it for 20 degrees deflection, and that's right here. And I popped up this data, and I was very interested to see what happens to the lift curve slope here on the upper right, because I expect it to move to the left and up. To see the increase in lift that I get from deploying that flap that is a large percentage of chord, I expected to see a big jump in CL, but I didn't. And I looked at this and I went, holy cow, what's going on? Look at this. They had a stall angle of attack about 10 degrees. Now the stall angle of attack is 5 degrees or less. The stall looks like it actually starts around 2.5 or 3 degrees, and a modest increase in lift. It went from 1.4 to 1. I'll give them benefit of the doubt that they make it all the way over to here, maybe 1.7. So 3/10 on the CL, and the lift curve slope is flatter. Like, wow, that. And I went and fiddled with this because I was very surprised to see the data look like this. Now, if you worked with a lot of these programs and a lot of airfoil data, this would come as a shocker. If you've never seen this stuff before, you go, oh, what's the big deal, Raul? I don't see any. Well, what's so unusual about that? Well, then you look down here at CL over CD, and normally this green curve here with the flap down, I'd expect to see that over here, kind of in line with the red dots. It's like, what the heck is it doing way over here to the right? Way over to the right. So what I got is I got a little bit more lift and a boatload more drag. It's like, this isn't a flap, it's a speed brake, it's an air brake. All it does is generate a lot of drag. Yeah, it gave me a little kink up in my lift curve, but man, if you want to generate drag, this is the way to do it. Bend your airfoil in half, right at the halfway point, bend it, you get plenty of drag. And then that's proven out over here on the CL over CD curve. Look what happens to that. They're up here at 110, and you put the flap down 20 degrees, and what do you get? 20? A factor of 5 difference? Wow. Your L over D just went in the tank. It's horrible. So the apocryphal information of pilots on the Flair saying it had poor performance, it was doggy, probably pretty much spot on, because if they put the flap down 20 degrees or even 10 degrees to foot launch, and they're up and they're going, wow, my sink rate is tremendous. I'm coming out of the sky. I'm going really fast. This is kind of doggy. My flex wing is better than this. This is why. Because that flap that is 45% of chord is generating a boatload of drag, and it's ruining the L over D. And on top of that, it's causing a very strong nose down pitching moment. It went from minus 0.047, I think is what we had, all the way to minus 0.18, 0.17, yeah, not quite 0.18, 0.175. Huge nose down pitching moment. Now, does that mean that the elevons couldn't counteract this pitching moment? No, they have different moment arms on the aircraft. They have different areas. You got two elevons, you got the two flaps. I don't know. You would have to put in considerable up elevon in order to counteract this much nose down pitching moment. How much? I don't know. I'd have to go do those runs, but I already know the final answer, so I'm not going to go do those runs. We do see pictures of the Flair flying nicely with the flap down. Different flights, different angles. Very difficult to ascertain what the actual angle of the elevons are. It appears to me that the elevons are up. We just don't know how much. And that's because the elevon and flaps are butted right together, and we tend to look at the V-shaped open area between the flap and the elevon and judge an angle from that. We don't know how much of that angle is due to flap and how much is due to the elevons. So we really don't have a good measurement on that. But we do have good data here, and we know that we now know that you put the flap down on the Flair, you ruined the performance. Geez, what could be causing that? And the only thing that's different about this flap than other flaps is where it's hinged. It's hinged at a very significant percentage of chord. Like, wow. So the best way to understand these situations is to do a parametric study. What happens when I take a hinge line that's near the trailing edge and then move it forward, all for the same flap deflection? What happens to the performance? Well, let's go take a look at that. So let's go to the Flair that has a 20, where the flap is 10% of chord. So the hinge line is 90% of the way from the leading edge to the trailing edge. It's just 10% of the trailing edge is the flap, and let's deflect it 20 degrees because we want to compare apples to apples. We're going to have the same deflection on all the flaps. And there's that data. Oh, look, here's what I was looking to find all along. This data here, lower right curve, the lighter green, that's with the flap being only 10% of chord and not 45% of chord. And look, we keep the nice low drag, and we get a nice bump up in the lift up to almost 1.8, rounds over reasonably well, without all the attending drag that you got from having it hinged way up at 45%. So this is your classic physics problem of law of diminishing returns. Just because you made the flap bigger in chord doesn't mean you have better flap performance, doesn't mean you can fly slower. What it means in this case is you get a lousy L over D. So you put the flap down 20 degrees and it's only 10% of chord, you actually get a bump up in your L over D, and it occurs just at a lower angle of attack, somewhere around, oh, what do I got here? What's it showing? About 3.5 degrees here. So that'd be not too bad. I mean, it's not a good airfoil to start with, but a flap deflected 20 degrees near the trailing edge would actually help you out. You got a better L over D, and your stall angle of attack, well, once again, it's going up here and it's kind of wandering off. It's a mushy stall. It's kind of hard to say where. So you could say, well, where it really breaks right here, where it stops climbing and heads down, that's the stall. Well, you're still at 10 degrees. I can still get up to a 10-degree angle of attack and pull some lift. It's just that much past 6 degrees, you're not gaining much lift. You're gaining drag. But you can get up here to 10 degrees before you really have a break in the stall, where the nose just literally drops down and starts flying again. So that's interesting. It's got better stall performance. It's got better L over D. And the pitching moment curve. Oh, that's interesting. Down here on the lower left, I got a flap that's 10% of chord, and it's deflected 20 degrees. And now we see something that stays, it's got more nose down pitching moment than the big flap. The one that has larger chord has less nose down pitching moment, but it stays a little bit flatter until you're up here at 5 degrees, and then it starts to climb up again. And actually, as you approach stall, you're back up around to a medium amount of nose down pitching moment. So overall, this is the kind of data that I would expect to see, but that's hinged at a different point. So let's go look at the other ones. Let's go look at, here's a 15% of chord, here's a 20% of chord, here's 25% of chord, here's 30% of chord, here's 40% of chord. And if you watch those as I did them, once we get past 30% of chord, the data goes south in a hurry. You start getting a lot of drag and not much more lift. And you start ruining the L over D kind of quickly. You know, here was 10%, 20%, excuse me, 10%, 15%, 20%, 25%, 30%, and then once you go past 30%, wow, then you really get flattened out down here and down here. So with this giant flap that they had on this thing in terms of its chord length, 45%, all they've done is ruin the performance of the aircraft and create a lot of drag. In fact, this data says that you probably don't want to go much past, let's see, there's 10, 15, 20. You take your first big hit somewhere between 20 and 25. There might be a purpose to go to 25% of chord, but you wouldn't go past that. You wouldn't go to 25. You're losing a lot of performance. And in the aero engineering world, this is somewhat known. Not everybody is aware of this fact. And that's because when you're trained to design aircraft, the professor will stand up there and say, well, you know, to size your ailerons or your flaps, just start out with a chord of 20%. 20% of the total chord would be the chord of the control surface. And the reason that the professor says that is because that's a best practice. It's a known number that works, 20%. And that's one of the problems that they had on the Flair project, is they did not follow best practices. And they didn't follow best practices because they wanted to innovate. And anytime you innovate, you take risk. And they delved into territory that was not best practices, and at that point, you're on your own. There's not a lot of data out there. Nobody's going to be able to tell you whether it's right or wrong. If they would have had this program and run it like I've run it here, they would have looked at this data. If they were smart, they would go, uh-oh, I better go back here to about 25% of chord or whatever. But they had that other factor. They wanted to fold it in half for transportation. And they must have had opposing forces. If somebody did run this code and said, oh, if you put the hinge line at 45%, we're going to have horrible L over D, even for relatively small deflections of the flap. And somebody else is saying, yeah, but I want to fold it in half for transportation. And the other guy says, what do you say we just put a pin in there, and for transportation we split it in half, but we have the control surfaces back at 15% of chord. Oh, that's too complicated. That's two hinge lines. I got cables cutting across the hinge line. No, it needs to serve multiple functions. It has to be elegant. It all has to be the same hinge line. And they might have talked themselves into a hidden design flaw that was deadly. And that's a darn shame. Or it could have just been the fact that they all looked at it and went, hey, that's pretty cool. Great idea. Look, it folds up small. It's also the hinge line for the controls, and let's go build it. Because if you look at a wing and you look at the hinge line, it's not intuitively obvious that if I move the hinge line forward, I'm going to ruin the performance of my wing. That's not the first thing that pops into your head. And if you're an aero engineer, you wouldn't even think to put the hinge line at 50% because none of your professors have ever told you to do that. So there we go. And if we want to back up on these, we can take them back out the other way and find out, actually let's go the other way, find out what might have been optimum. That one. So it's somewhere between, I'm on the upper right now, it's somewhere between this kind of orangish yellowish line and the purple one here. That's 30. That's 30% of chord. That is 25% of chord. So let's turn the other ones off. doom, doom, doom. So this is about your best bump and lift, but you have much lower angle of attack of stall, and you have mediocre L over D. So and what I know from Steve Morse on the Swift is they selected 20% accord for the Swift, and I'll go show you that now, because they knew that's where they would get the best performance and have the least amount of problems on other factors. And look, here's the Swift airfoil. I'll turn the no flap one on. So there's no flap and flap on the Swift airfoil, and they're going from a little less than 1.6 maximum CL, I'm on the lower right graph, all the way up to here, which is 2. So they're going from less than 1.6 all the way up to 2 for almost no additional drag. And that's because they're hinged at 20% instead of 45% or 50%. So hinging way far forward on any airfoil is a bad idea because it ruins your performance. And as you're going to see here in a moment, it causes other problems. Let's see, do I have that for mine? And just to prove to you this happens on any airfoil, here's my airfoil if I hinged it at 45% and deflected at 20 degrees. And I'll turn my original one on also. I'll turn the Swift back off. And we can see the same kind of thing. Here's my original airfoil right back here. It's curved. Deflect the flap 20 degrees when it's hinged at 45%. Look where the drag goes. It goes way over to the right. It doesn't stay here and go up higher CL with no more additional drag. No, we make a quick jog to the right, and then the CL goes up as the CD goes up. So it really ruins my performance. My L over D goes way down here. You hinge an airfoil much forward of 20–25% of the chord, and you ruin the performance of that airfoil. Bigger is not better. And that's why anytime you hear anybody use intuition to describe why they did a particular design, take it with a giant grain of salt. When you hear the saying, if it looks right, it'll fly right. Oh man, that is just so not true. Or, you know, I felt that if I did this, that would be good because of that. And you better ask that person, do you have data to prove that? Because intuition doesn't carry the day in this game. In fact, intuition is opposite here. I need a bigger flap to really slow up. No, you need a long, skinny one at the trailing edge. That's what you need. So, big mistake. Might have put that hinge line there just out of intuition and thought, oh, handy for transportation too. Who knows? But it was just a wrong decision. And let me show you why it was really, really wrong and turned deadly. I wanted to take a moment here to discuss the impact of pilot weight on the Flair aircraft. I put together a little cheat sheet spreadsheet here to do this work. I'm looking at coefficients of lift across the top here, and for various weights, I get a output of how fast the aircraft would have to fly to carry that weight. Now, I want to talk about this in terms of coefficient of lift for the sectional airfoil. Now, we know that the whole aircraft cannot pull that high a CL because there's twist in the wing, washout in the wing. So it'll never, and you know, normal aerodynamics means that the wing is not going to pull that maximum lift coefficient. But I'm using this spreadsheet for comparison purposes on various aircraft or flight weights, gross weights. So we just pick a CL that we want to fly at and say, what speed am I flying at? So in the literature I saw, they promoted the Flair as going as low as 30 kilometers an hour for landing with a flap down. Now we know that with a flap down 20 degrees, that's a reasonable amount. You're not going to get much more bump and lift from what we've seen in the other data. You're going to pull an At best, you might get close to a CL at 1.8, which is around here, around 35 kilometers per hour. Well, 35 is not 30. So they had promoted numbers that, according to analysis, are just not achievable. Not with the average pilot weight. And here I have a 60 kilogram pilot at this point in this analysis, right over here, 60 kilograms. And I got him 50 kilograms for the aircraft. Did it really weigh 50 kilograms? I don't know. They wanted it to weigh 40, and we know that they were they said they were on a program to lightweight the vehicle to get it down to 40. So we'll assume for now that they were a little on the heavy side. 50 kilograms. 50 kilograms would be pretty much spot on for what you could build that thing at and be structurally sound at that era. So I'm using 50. Even if we took it down to 40, if I put 40 in here, it doesn't help much. Oops, why did it do that? If I put 40 in here, it's not going to help that much. So you'd have to pull a CL of 2, which they couldn't do, not with that aircraft. We've seen the data now, and we know that the aircraft is going to be less capable than the section. The airfoil section will never pull a CL of 2. So even if the aircraft weighed 40 kilograms, you still can't get there. So I'll leave it at 40 for now. I have a pilot weight of 160 kilograms in here. That's about a 135-pound pilot. You know, you're a skinny teenager, about correct for that. And here's the numbers. You know, if the aircraft could pull a CL at 1.4 or even 1.6, your speeds are between, we'll just say, let's say with a flap down, the aircraft could pull the maximum coefficient of lift for an unflapped airfoil section, because we have to knock off for washout and other stuff. So maybe they might have been able to get the thing down to 36 kilometers per hour, 37 kilometers per hour. Now, if you're a new pilot coming in, somebody's going to give you a little briefing, I hope, that says takes off at this speed, stalls at this speed, final approach at this speed, flare to land. And they would give you basically speeds to fly. They might have been placarded on the vehicle. Quite often in certified aircraft, you'll find a placard that says these are the speeds to fly. So they would have told them 35, 36 kilometers per hour, 37. And then the new pilot gets on board and he weighs 20 kilograms more. Okay. So he weighs, now we're up to 80 on the pilot. Now, before, we go back one, let's go back one. So if he's pulling 1.4, 37 kilometers per hour. So maybe somebody told him, you know, keep it above 35 kilometers per hour, keep it above 37. Who knows what they might have told him, but it's somewhere in that range. And then if you're 20 kilograms heavier and somebody's told you 37, where is 37? 37 is out in here. You have to pull a CL of 1.75. Even the flapped airfoil section is not going to get you there. So this could be very well why the pilot was saying, I'm having a hard time trimming the aircraft. Somebody told him final approach is at 37 kilometers per hour, but he can't get it to fly that slow because he's 40 pounds heavier, 20 kilograms heavier. And nobody stopped to think, oh, if you're heavier, it's going to fly faster. You're going to have a faster approach speed. In fact, his approach speed is going to be more like, if we said he could pull 1.4, he's going 40 kilometers per hour. That's 3 kilometers per hour higher. And that's enough to notice. You know, when your flight speed is 40 kilometers per hour and you have to fly 3 or 4 kilometers per hour faster just to avoid stalling, or to trim the aircraft, that's 10%. Pilots are going to notice a 10% difference. So if he's trying to get it slowed up down to 37, but he can't because he weighs so much more, oh, that's a problem. And that could cause somebody to dump flap in a big hurry, or put even more flap in, more than 20, maybe put in 30 or 40. And no matter how you look at it, it's just worse and worse and worse. The only thing that he could have done here is fly the aircraft faster and land faster. And maybe they didn't really just stop to think. The increase in pilot weight, that 20 kilograms difference between the previous pilot and the current one, represented 50% the weight of the aircraft. It's huge. It's a huge difference. And that makes aircraft fly different, both in terms of weight and balance and speeds to fly. And were they careful enough to stop and do the calculations and find out how much faster he'd have to fly? And how they might have to trim the aircraft differently? I don't know. But just knowing that the pilot was 20 kilograms, 40 pounds plus heavier, probably made all the difference. And that's probably why they were able to fly for 50 hours and not have a problem. And you got a heavier pilot, he's been told certain numbers, and he's trying to get the thing slowed up to land, and he dumps a bunch of flap, and then we've looked at the other data, we see what happens when he does that. So there's another clue as to what could have caused this crash after 50 hours of flying. So here we are back at the data. Now, this is undeflected flap, and we know he's trying to slow it up to a speed that he's been told, and he's pushing up here towards stall. He's running around near stall. He's at, and I'm on the upper right curve, and he's pushing, 9-degree angle of attack. So his mean aerodynamic chord is somewhere around 9 degrees. The root is even higher. The root of the wing might be operating in a stall in this mushy area over here to the right of the stall. And he doesn't know that because he's not getting a significant burble from separated flow, because this airfoil just kind of mushes along at that angle of attack. There's no break in the stall. So the inboard part of the wing might be stalled, and the majority of the wing is still flying. He's up at a high angle of attack though. And he's trying to get he can't get it slowed up. Not with elevator. So he puts down 10 degrees of flap to try to slow up. And let's see what happens. Let's turn that one on. Let's go over here and turn it on. There's 10 degrees of flap. Let's turn on 20. There's 20. So he says, I can't trim. I'm running on elevator. So he puts the nose back down and picks up a little bit of speed. And his required CL goes down. Right now he's flying at a lower angle of attack. Now I'm flying at a lift coefficient of 1.3 down in here, and I'm at a 7-degree angle of attack. Now this would not be unusual. My wing operates at about an 8-degree angle of attack on average, but my 8-degree angle of attack is 8 degrees away from a stall. He's operating kind of the same way at this point. He's got the nose back down. He's picked up some speed. He's got the glider cleaned up. He's trying to get it to trim. And he's only 3 degrees away from a stall, 2 or 3 degrees away from a stall. That's okay. You could fly like that all day. You'd be fine. He's heavier. He has to fly at a higher speed. He wants to get back. He wants to get that 40 kilometers per hour or less. So he puts out 10 degrees of flap. Well, now the airfoil is operating way over here. He goes from here to over here. Now, if I'm flying at a 7-degree angle of attack on average, I'm right about here on this curve, right where this crosshair is. I think you got a little pointer. So I'm flying at a lift coefficient of just over 1.2 at a 7-degree angle of attack, and I drop 10 degrees of flap. And what happens? Well, if the span of my flap was only 10% of my wing, not much happens because the majority of the wing is still flying at that angle of attack. But if your flap is 2/3 of your wing, you've now magically morphed your wing into something entirely different than what you took off with. And here's what happens. You go from this curve, the red curve at 1.7, and remember, the aircraft is dynamic. It has inertia, momentum, and all that, and the flap's going to go down quick, but the aircraft is not going to pitch differently very rapidly. So you go from here on the curve straight up to where the flap is, and you're well into a stall. You're at a higher CL. You go from 1.2 to 1.6 on the CL, but you're past stall. And this airfoil does not have a clean stall on it. So you're burbling along here in this stall, and you still can't get it to trim. You're pulling lift, but the nose doesn't go down a lot, but it doesn't go up, and you certainly don't slow up, and your lift curve uh, has gone up. Let's see, which one do I have turned on? Yeah, that's the right one. But your stall angle of attack has gone way down. So at this point, if I were the pilot on this aircraft and I'd done that, I think I'm in a mushing stall. If it were a powered aircraft, they'd call it on the backside of the power curve. That you got to get the nose down, but how do you do that? I don't have enough power. Well, in a glider, you would. You just shove the elevons down, and you might get the nose back down and get flying again. But you've literally jumped from a flying configuration to a stalled configuration instantaneously. And that's because that darn flap is hinged so far forward, such a big percentage of chord. So suppose he got lucky, he's on final approach, and he goes through this cycle once. He says, oh, I'm having a hard time trimming this thing, and so forth and so on. And then he decides, okay, I'm going to get this thing slowed up. I'm not going to come screaming in with my nose 5 inches off the ground at 50 miles an hour. I'm going to get slowed up. And he has it cleaned up, and he has it trimmed out. He says, I just need more flap. And he decides, I am going to dump flap. I'm going to go 30 degrees. And he's here on the curve, and now his stall angle of attack is at 0 degrees, and he was at 7. So the glider is going to want to pitch as fast as it can from 7 degrees to 0 to get flying again. And that would happen almost instantaneously. It would be equivalent to doing an accelerated stall on a regular glider, where you've pulled the nose way up and the speed bleeds off until all of a sudden it breaks into a stall. But he's done that by deploying the flap and shoved himself right into the other side of the stall curve. Stalls way back here at practically a 0 degree angle of attack with the flap down 30 degrees. Suppose he only did 20. Oh, well, 20 stalls over here at about 3 degrees, and he's at 7. Maybe 20 was enough to do the trick. But literally, by deploying the flap, he stalled the entire glider. And that's because the flap was 2/3 the span of the wing. Another really poor idea. Bigger is not always better. So with a hinge point way far forward and the flap representing the majority of the flying surface of the aircraft, and he dumps the flap, loses all his lift. Excuse me, I said that wrong. He dumps the flap and reduces the stall angle of attack down to a very small number, and he just turns the aircraft into a brick. He tries to counteract these by pulling full up elevator, which then dumps what remaining lift he has out on the wingtips down to essentially 0. So he dumps the flap, pulls in elevator, and loses all the lift that's on the wing. All of it just goes to nothing because he's totally stalled. The entire wing is not flying. And that's when you go to sudden nose down, vertical, straight into the ground. Because you're not a glider anymore. You're a collection of composite parts that's a brick. It's not generating lift because you've taken it way past its stall by dumping the flap. And as you'll see in my layman's explanation later, you'll see the geometry of how that actually happens. Now, is that something that they could have spotted ahead of time just by looking at the thing? I don't think so. I think that they were on a path to do a particular thing, and they did not have a specified test plan that they followed, and they didn't follow standard testing procedures. And they stretched into an area that went well beyond best practices and took risk, and they weren't prepared to deal with that risk. And they took all that risk all at once with a new pilot that was heavier, couldn't fly as slow as the lighter pilots, put the aircraft into a configuration that had never been tested before he got into it. And he found the configuration that was the fatal configuration. Who knows, the lighter pilots may never have gone to 30 degrees of flap deflection. Maybe they had. Maybe they had deployed it slowly. Another scenario that I can think of that has happened to me many times. Imagine you're the heavier pilot, you're flying this thing, you're trying to get it trimmed, you're on final approach, to the glider field where all your buddies are watching and you run into lift. I can't tell you how many times I have run into strong lift right on final approach, and it just burns you every time. You just go, oh, damn it, and you got to pull on more spoiler. Well, he didn't have spoilers to put on. All he has is the flap. And he's got to get the thing on the ground. And he doesn't want to overshoot the runway. He doesn't want to look like a lousy pilot. He's got to land it on the spot. And if I were there and all of a sudden I hit a bunch of lift, well, can I side slip it? No, it's a stinking flying wing. There is no side slip. There's no way to create drag by flying sideways. All you can do is dump more flap to try to get it on the ground. And in this case, that succeeds. If you dump more flap here, you're going to get yourself on the ground in about 3 seconds, going vertical, straight down. And that's because of where the control surfaces are hinged. That was the big mistake. So I'll say it later and I'll say it here. Never, never, never hinge your control surfaces forward any more than, say, 25% the chord of the flying surface. And that could be a tail, a wing, anything. So here I've set up a print of the Flair airfoil, both in its base configuration with the flap deployed, and I've taped it up here on my whiteboard because I didn't want to have to try to redraw it all. And I put in some relative wind. And I hope that this explanation is more intuitively obvious than what I showed you in the actual aerodynamic data, the computational fluid dynamics, to show you how a stall can occur just by deploying the flap. So if in the clean configuration here, the chord line runs from the furthest point forward, furthest point aft, and the angle of attack is this angle down to wherever the relative wind is, okay? Now, these airfoils are parallel to each other on this page. They're printed that way. And the only difference is the deflection of the flap. But look what happens when you deflect the flap. Where's the chord line? Furthest point forward, furthest point aft. That's always the chord line. And the angle of attack is to the relative wind, which is the same. These are parallel to each other. Well, you've moved, by dropping the flap, you've moved the chord line down. You've increased the angle of attack of the wing by deflecting the flap. Now, when your flap is only 10 or 15% of the airfoil, that angle change is relatively minor. But if you hinge it up here at the halfway point and you drop the flap, the chord line moves a lot. You're changing the angle of attack of the wing every time you deploy the flap. And you have to go look at it this way and go, oh, I see. I haven't pitched the aircraft up or down. I have done nothing with the flight path of the aircraft. It's going along like this just fine. And I put the flap down, and holy cow, now I'm at a much higher angle of attack. And if this is already close to stall, well, this will go right past stall, just like I showed you in the data. If he was trying to slow up for landing and he's working around the stall area because he's trying to get it slowed up and he drops a little bit more flap, boom, stalled wing. And if your flap is 2/3 of your wing, you just stalled 2/3 of your wing and you fall out of the sky, especially if the elevons are up and not generating any lift out at the tips. Heck of a deal, isn't it? Hard to believe. I deployed the flap and I stalled my aircraft because you're essentially morphing the wing. It's one thing to put down a little flap back here. It's another thing to bend the airfoil in half. You're completely changing the design of the aircraft in flight. By the flick of a lever, you now have a highly cambered airfoil that's at a totally new angle of attack. Another way of looking at this phenomena is to take the arrangement to a logical extreme. Can you imagine if you had the ability to hinge, if the hinge for the flap were the leading edge of the wing, not back here, not the halfway point, but all the way up the leading edge, and I deploy my flap. Well, there, I'm putting the whole airfoil up at a higher angle of attack. So if the angle of attack for this for stall on this airfoil is 16 degrees, and I deploy my flap 20 degrees, I've stalled the airfoil. It's that simple. That's why the root cause of this accident is the location of the hinge point. This proves true for any airfoil. Any airfoil will have this problem. And I've shown you the data that says it's better to stop at 20% because you're going to lose a lot of performance as you move forward. And you get to a point up here where, oh, I'm morphing my wing, or you hinge it at the leading edge such that every time you deploy the flap, you're drastically changing the angle of attack of your wing, 2/3 of your wing. The root cause was not separated flow. The root cause is not necessarily running out of elevator command, although those two factors could have been contributors. The root cause of this accident was the placement of that hinge point and having a flap that's 2/3 of your wing. If the flap had only been 5% of the wing, yeah, you stall that much of the wing, you got plenty of wings still flying to recover. But when your flap is 2/3 of your wing and you change its angle of attack in mid-flight by putting the flap down, so all of a sudden here you're flying at 7 degrees, and down here all of a sudden you're flying at 12 degrees. You've stalled the wing. And to drive this point home, I know it's a mundane answer. What caused this crash? It stalled. Everybody like, oh. Everybody likes to hear all those fancy, separated flow and this, that, and the other thing, and specialized flying wing problems about flaps and pitching moments and elevons and yeah. This was a stall. It was like doing an accelerated stall. The way in which this aircraft was stalled by deflecting the flap down, it created this equivalent of an accelerated stall that you would do in a glider, and there just wasn't sufficient altitude to recover from it, to regain speed, and would have had to pull up the flap anyway. It just wasn't time to do all of that. Even if he had gotten the flap up instantly, he still wouldn't have recovered because he's going to have to regain flying speed until his relative wind is oriented where he's at a positive angle of attack below stall. So, unrecoverable. I know people will never let go of their thoughts about it was separated flow on the elevon. It might have contributed to this. This does explain how you end up like this. How do you get into this configuration? You stall. Does that make this the root cause of the crash? No. The stall is the root cause of the crash. It's the thing that happened first. And put it into a configuration somewhat like this. And maybe the flow separated off the elevon, maybe it didn't. Was it the huge flap overpowering the elevons? Well, that's what made it difficult to trim up front. It's not what caused the stall. Okay? It's just plain, ordinary old stall because they had the ability to morph the airfoil, totally different airfoil, by hinging it way far forward like this. Right back to the saying, bigger isn't always better. Certainly not in this case. So, if you have any doubts, I know people are going to want to hold on to their beliefs that they've had for 30 years on this crash, but now is the time to start letting go. And to help you let go, if you have any doubts about all the data that I've showed you and all the hours of video we've been through, I'll read you. I'll let Steve Morris have the closing words here. Well, not exactly the last word. Sorry, Steve, I'd never let you have the last word. But Steve wrote to me. He says, regarding the Flair 30 stalling with flap deflection is well known on the Swift. And I didn't know this about the Swift. And we always deploy the flaps on the Swift at speeds above stall. So when you're landing the Swift, you don't fly it anywhere near stall speed. You keep it above stall speed so you can deploy the flaps without stalling the wing. So he says right here, the Swift will exhibit similar characteristics. If you do add flap while flying slowly, it will stall but recovers quickly. At most, and their flap's only 20% of the chord, not half. At most, some pilots have a hard landing due to dropping the flaps when flying slow in ground effect, but this hasn't been a problem with the Swift. All bets are off with the Flair 30 since I don't know what their flap was doing in flight. It seems like any flap deployment would cause a huge nose down trim, as would a stall. So Steve's saying that if you had a sudden flap deployment on this, just the pitching moments that are involved and running out of elevator would cause a rapid nose down, as would a stall. And what I've shown you with the data is that it's most likely the stall. Because you're flying near stall and you need to get slowed up, and you put down a little bit more flap, and boom, you go right to the stall angle attack for this, oh, Frankenstein monster of an airfoil that happens when you hinge it halfway. So, bottom line on the whole thing is, don't hinge control surfaces forward of about 30% of chord. Any further forward than that, you're ruining the performance of the airfoil and putting yourself in danger of inducing a stall due to control deflections. And that's all there is to it. I wish I had a smoother answer, something more exciting, but I don't. It's just a stall. We know what not to do. At least we have a solid lesson learned. If you're a designer, and this applied to model aircraft, full-size aircraft, don't ever do this. Do not do this. There's a reason why you don't see it on aircraft, and that's where the real problem occurred with the Flair, is that they did something new, and in the engineering world, we would call this not a best practice. And it's not because it's a bad practice, it's not a best practice because there's no data on it. There are no aircraft flying around with this type of configuration. And anytime you do something new like that, you take a risk. And that's where we run into human factors and the final part of this series of videos explaining the true root cause. I just gave you the technical root cause and told you what not to do. And now I'm going to give you the real bottom line root cause, which is human factors. Hello, welcome on back. I have some notes with me here because we're now going to delve into the area which is not very linear in nature, and I've tried to make it that way to get messages across to my viewers. It's also a very difficult topic, not in terms of its technical complexity, but in terms of getting people to understand, absorb, and accept the messages. A lot of people don't want to hear this stuff, and there's a variety of reasons for that. But these are really common problems and can affect any aircraft development program. Little, huge, fully professional, totally amateur. Can happen to anybody. I got some notes here to help guide me through, and you'll be able to read this stuff on the whiteboard behind me here while I ramble on over here. Choose which one you want to pay attention to. It's up to you. So, I want to make very clear the reason why I'm making this video. I'm not here to disparage anybody at all. Many times when you delve into human factors, it becomes a blame game. That's not what this is about. This is about emphasizing the need for safety when you do aircraft development and how we go about achieving those levels of safety. Let's see. And I don't want to disparage any of the memories that people have of people that were on this team. There's a number of people that were involved in this program. They're long gone now. It really doesn't matter so much as to who they were. I hear they were all nice people. But it is important what they did or what they chose to not do. And that's where the lessons learned lie for us who are still here in developing aircraft. So I decided to analyze this crash so I could, if I could find anything to help me with my current project. And what I found was very common stuff that really would apply to anybody doing this type of work. I'm hoping to put out a message to engineers, especially young engineers. If you're young and just getting into this, if you're a student, listen up. This is probably some of the most important stuff you will cover in your career, and nobody's going to teach you about it formally. You might end up being involved in a group that's doing it, or you might find it interesting, but when I was in school, there weren't any classes on this stuff. There could have been, but there weren't. So our jobs as engineers, in my mind, I said it once as a quote from a newspaper once. I said that engineers should dedicate their lives to improving the technical aspects of the human condition. And I was too young at the time to realize an important part of that is to do so safely. Obviously, you're not improving the human condition if people die in the process. And there are methodologies, processes, and procedures to follow to maintain safety while you do an endeavor of this type. And at that, I really want to say, despite what people think, and as much fun as it is, developing new aircraft designs is extremely dangerous. Really, really dangerous. And that danger sometimes goes hidden. We don't even know it's lying there. It's like a booby trap. And the reason that we do these processes and procedures is so that we can identify the booby traps and carefully step around them or carefully remove them. But still, even with the utmost care, this is risky business. And I'll put up a poster here over my face, full screen, give you a moment to read it. That poster, although often used for amusement purposes, is very profound. The words on that poster are 100% correct. And as engineers and developers of aircraft, we should heed those words at all times. And as pilots also, or builders. This is not an area of work which is tolerant of screwing up or cutting corners. And it requires great discipline and at times great humility. Okay, what else we got here? Let's see. Okay, so when we're developing a new design, we're always seeking some type of glory. I couldn't think of a better word for it. We want to fly higher, faster, further, lighter weight aircraft, more efficient, less expensive. That's all the glory. And the issue is, let's see, what did I write to myself here? Oh, in order to achieve that, anytime we want to achieve those types of goals, we have to take risks. We have to do things in a new way. We have to do things differently, sometimes quite differently, in order to make that big step forward, get over a hurdle, and do the next great thing. And anytime we do that, we take risk. So development of aircraft is way more than just the engineering calculations and structural tests and other stuff. It is the management of risk as you go through these processes. And sometimes it's boring, sometimes it's really expensive, and usually it will delay the project. And we never like to be delayed. All of what I just said is especially true of flying wings. There have been so few flying wing designs done in the span of aviation history compared to conventional aircraft. Flying wings, dozens. Conventional aircraft, thousands. So the database we have for conventional aircraft is huge by comparison. And I always like to remind myself, we know nothing about flying wings, next to nothing. And I myself, I probably know nothing about flying wings. And I've been designing flying wings for more than 45 years. And the more I design them, the more I realize we don't know anything about them. There's all kinds of hidden little tricks in there, and you're going to trip over stuff, and you can't look it up in a book. And what few books there are, I've found to be iffy at best in terms of the technical information that's in them. Okay. Let's see, what else was there? Yeah. Okay. So as aircraft engineers, our main job, it's our job to generate a well-tested flight envelope that defines the region in which the pilot can operate that aircraft safely. That's our job. And there's a way to go about doing that. And I would have to, from the things that I've seen, I'd have to venture a guess that on the Flair program, many of those things were not done. Why, I don't know. So, let's see. Key part of aircraft design is, I always like to tell people this because it makes them laugh. Don't do stupid stuff. And then people chuckle a little. I go, no, I'm serious. We all know what the stupid stuff is, but we continue to do it. And we've been told by other people, well, that'd be dumb. But I'm innovating. I have to innovate to move forward. I'm trying to move the state of the art forward. I have to innovate. And they go, well, that's really kind of stupid, you know? And then we get offended. And you go, well, screw you. You don't know what you're talking about. I'm going to go do it anyway. Because that's one of the human factors. We don't like, We think we're smart. We think we know what we're doing. We have goals. We have a plan on how to get to that goal. And somebody comes along and says, by the way, did you think of this? And we think about it for a second. We go, oh. And we just know immediately it's bad news. Somebody thought of something that we didn't think of. And it's not only personally embarrassing and disheartening, and then we know it's going to hold our program back or kill it entirely. Maybe we were barking up the wrong tree. And it's awful. And rather than absorb that message of you've made an error or you were remiss and you overlooked something, and accepting that and saying, oh, shoot, we push back against other people. Nah, I know what I'm doing. I tested that. I looked at that. I ran a computer program that said thus and such. And then somebody will say, well, how do you know the computer program's any good? And I've had it happen to me personally. I've had people come to me and say, are you sure it works that way? I go, yeah, absolutely. I've been flying it for years. Works great. I don't think so. I don't know what you're talking about. Then they come back with a mathematical analysis, and I have to look at the math, and I look at it. It takes a while. And it's just like a spear through the heart. Math doesn't lie, and the math said, doesn't work the way that I thought it worked. Well, and it took me a week or so, but I had to let go of it. Never argue with the math, and always be ready, always carry enough humility with yourself to allow other people to come up and tell you that maybe what you're doing is wrong. And anytime during the development of anything like this, anytime somebody says, are you sure that's right? You better just stop right in your tracks and double check. It could be some moron off the street and they don't know what they're talking about. And if that's the case, and it only takes you a split second to say, oh, no, they don't understand the physics, the actual real physics that we know, and I have data that says that what they're worried about is not a problem. Or they might say, it might be somebody who's an engineer, you don't know they're an engineer, and they say, have you thought about this? And you better stop and think about it, do the calculations that are required, and double, triple, quadruple check your work to make sure that you're not doing the stupid stuff. Okay, let's see. So, as I said, to avoid the stupid stuff, we follow best practices. There are processes and procedures for doing this work safely. What else did I throw in here? We follow best practices. Okay, so now, best practices, lots of people are familiar with engineering best practices, how to develop a design by using certain equations, make calculations, make sure you have the pitching moment correct and all this other stuff. You run it through a code if you don't want to do it by hand. And those are best practices. You need these types of numbers to achieve this stability goal or something like that. There's a whole slew of best practices that most engineers don't know about because they don't like to talk about it, they don't like to do it. And that's human factors. And human factors can actually be a bigger driver on your project than the engineering side, than the clean, pure mathematical engineering side. And the reason engineers don't like to talk about human factors is you can't calculate them, you can't control it precisely, and there's no exact right or wrong answer. But we still have best practices for trying to attenuate the impact that human factors can have on a project like this. So, managing human factors, doing human factors on a project like this, like managing a blob of slime, you got something that's running out over here, you got to plop it back in and bring it back in over here, and you got to herd it in a general direction. And sometimes it's maddening, it's very frustrating. But if you're more of a shepherd than a driver, then it can be a manageable task to deal with human factors. One of the big problems with human factors is people that do this type of work have huge personalities. I'm sure you know that I do. I wouldn't get on YouTube and do all this stuff if I didn't have a huge personality, plenty of ego, all that other good stuff. But I want to get my messages out to people out there about how to do this type of work. And we've gotten to a point where we have to discuss something that's really critical that doesn't really involve engineering. And I hope to get across that even though there are huge personalities involved, if you can find a way to always carry that humility with you and tell yourself, I'm probably wrong, before you even start, say, oh, I'm probably wrong, but I'm going to try this. If you start out with the attitude of, I have this fabulous idea, it's going to be the best thing since sliced bread, watch me, you're already in trouble. In other words, don't be a glory seeker, be a problem solver and a risk reducer, and have your ears open all the time for negative feedback. And remember, negative feedback is not about you, the designer or builder or somebody that's working on the project. It's not personal. The negative feedback that comes in, those are people trying to help. And we need all the help we can get when we do this type of work. So when somebody comes up to you and says, you're wrong, they're not disparaging you. They're not saying you're a bad person. They're just saying that technically something's wrong here and maybe you need to take another look. So you swallow your pride and you go, okay, I'll take a second look. Anyway, so yeah, be prepared for negative feedback. Those people are just trying to help you. Let's see. So I've studied all of the printed material that I could get on the Flair 30 crash, and I've looked at it quite closely. I've actually spoken to several, or communicated with several people that were around when the aircraft was being designed and built and tested. And one of those was actually an employee of the company that was behind the development of the aircraft. And so these are people that have semi-direct knowledge. In terms of direct knowledge, I was told who those people are. Some of them are still living. Some of them have lots of information. The German government has some information. None of that stuff that could I get. I was never able to get A-level material on the subject. So given that, I've had to do a fair amount of speculation on what I have read and heard. And because it's speculation, that means I could be wrong. I could be totally wrong on this, but my speculation is based on, nearly 50 years of aero engineering experience, and that's in the U.S. aerospace industry. So I have a depth of experience that allows me to look at a project like this and go, oh, I recognize that problem, and I've seen that problem before, and oh, that path will take you down to a very bad place. And I've seen the types of actions and errors that occurred in the development of the Flair. I've seen those occur at the highest levels in the U.S. aerospace industry. Hundreds of engineers, all highly trained, involving billions of dollars, making the same types of mistakes. And that's because it's human factors. And humans really don't change that much. We all behave the way we behave. We all have our foibles, and those are human foibles. And as long as it's humans designing these vehicles, those problems are going to continue to exist. It's very hard to get this subject matter into people's heads such that they go, oh, on my next project, I'm not going to do that. Usually what you get is, oh, how stupid were they? I would never do anything that stupid. And then people proceed to do it. It's amazing how it happens. Okay, so in the U.S. aerospace industry, we have established processes and procedures for attenuating the impact of human factors. And sometimes they actually work. I've seen them work. I've seen them fail too. So if you want to understand the basics of the human factors that went into this crash, I'm going to send you over to a project, a program, not aviation related, and not try to explain it within this one. I'm going to tell you, go look at this other thing, read about it, read about how it happened, how it ended, and you will see examples of everything that I'm going to talk about here. And that project is the Titan submersible that was built to go take tourists down to go see the Titanic. I've tried to summarize here on the whiteboard the key factors that I noted, and they're here on the whiteboard. So now I can put down my notes and we'll take a look at the whiteboard. So I got here human factors. I put it into 4 categories. My wife thought that this was important that I try to categorize it. It was difficult at best. And I started to say before, and I'll go back and repeat. I've spoken with both my wife and daughter on this. They're both good outside viewpoints that'll give me a clear vision of what it is I'm trying to do, because this has been really hard. I've written 4 of these scripts to try to discuss this topic, and running between sad and depressed and rewriting it different ways, trying to figure out how to get people to understand it and accept it, has been a huge task for me. And they helped by whittling it down for me. And it came down to, what am I morally obligated to do? You know, a lot of the people involved with the project are long gone, so it's not going to make any difference there. And we know a lot more about flying wings now than we used to. Okay. But a person died. And there's a way to avoid that. That could have been avoided on this program. It would have involved a lot more work, but eminently doable. And we know how to do it. So I have a moral obligation. If I'm on YouTube trying to show people how you design and build aircraft, this is a part of it. So I have at least a moral obligation to stand up and say, hey, if you're doing this kind of work, pick up some books, ask other people, study about human factors, and learn how to control those as you go through your aircraft development. It's important. So they concluded that that was what I needed to do at a minimum level, was to at least wave the little flag and say, okay, I need to do my duty to the community of designers and say, here's a great way to go about having problems, and you'd be well served to avoid them. So I'm doing that. In terms of the technical aspects of this, there I can give one clean, straightforward answer and go, it's this. In fact, you saw that at the beginning of this video. And don't ever do this, because this is wrong then, wrong now, will always be wrong. And then engineers can go do their own calculations, go, oh yeah, I see it. Oh, okay, I won't ever do that. That usually works out pretty good. Yeah, and I gotta say, studying through this, finding this stuff and learning about this, the most shocking thing was how sad it made me for like days at a time. It's just like, oh God, it's that stuff again. And they didn't have to go through this. And we got 30 years of people believing it was this problem when it's really this problem over here. You know, yeah, there's a technical problem buried in there. They could have found it. They didn't know it was there. But what really did them in was the human factors. That's the root cause of this crash. Okay, so apparently they did not follow standard aircraft development practices, which you've heard me already allude to. And the main thing we do, I talked about flight envelopes. We do an incremental opening of the flight envelope, and that was probably not followed. How do I know that? Have I seen data, written reports, stuff like that? No, I haven't. But as an engineer who's done this for decades, I see what's missing, or some odd fact. And I go, oh, the only way that you could get there is if you went here, here, and here. And that's the only way to get there. So they have 50 flight hours on this aircraft. 50! That's a lot for a hang glider, foot-launched sailplane, light sailplane, whatever you want to call it. It's a lot of hours. And then it crashed. There's 2 potential causes for that. Number 1 is a control failure of some type. Something broke. But the way that the flight is described, that's probably didn't happen here, because the aircraft would have come out of the sky differently and impacted differently than the other factor. The second part, which is the most likely one, is that what caused the crash was a pileup of factors. It has to be this, and it has to be this, and it has to be this other thing. And when those 3 things are combined together, you'll fall out of the sky. And that usually has to do with control settings, deflections, rates. And if you have a standard aircraft test and development program, we're going to do A, B, and C and check this. If everything's good, we move on to part 2. And we go through these and through these. And those test programs are extensive, expensive, and take a long time. But you literally have to say, like with my wing, I have a test program that says I need to be able to fly at 20 feet off the ground and hold altitude steady when on tow. I need to be able to roll the vehicle side to side without touching the wingtips on the ground. I have to have precise control, right, when I'm on tow. Well, we've done those. Okay, so the next thing is I got to get up high enough where I can get off tow and do gentle turns. Maybe banked 5-10 degrees, do a 30-degree turn to the right, and then come back to the left, and maybe a little bit of maneuvering in pitch. If I can do shallow maneuvers precisely, then we can move forward. And there's a whole bunch of this that you go through. You got to test the speed range. You got to test your roll rates. You have to test your pitch rates. You have to test coordinated turns at different banks. You have to test the full range of control surface deflections. And you have to combine those with different speeds. So you get this matrix that's large. A lot of data points that you have to check. And it takes hours and hours and hours of flying to do that. They had 50 hours. If they flew for 50 hours, they should have had enough flying time to test the full range of all the stuff that I'm talking about. And they would have had their flight envelope fully opened. Flight envelopes start out as a dot. That's all you know about the aircraft. And then little by little we open them up until we get to a point where we have a defined space where a pilot can safely operate that aircraft. That's how they could get. How do you get to 50 hours without crashing and then crash? Well, you haven't tested the full range of your flight envelope. You haven't tested the full speed range, the full bank range, all your different control settings. Because if they had, it would have fallen out of the sky sooner. Not on final approach, 50 hours into the game. It has to be. They did not follow a standard open the flight envelope procedure. They just went out, flew around, and flew it like you fly a hang glider and say, it's good, I flew it, flies great. But there's this booby trap hidden in there, and they don't know about it because they haven't done the full matrix of test of ranges of configurations. They haven't done the full range of configurations on it. And the poor sap who went in and crashed with the thing tested a configuration that hadn't been tested before. And he paid the price. So, definite, straightforward clue, they did not have a regimented test program in place. They might have had it and not followed it. Oh, this thing's great, it flies super, let's get it on the market and start getting some of our money back. They might have done that and cut corners just as bad. That's another human factor, tendency to cut corners. Too much work, too hard, and we skip things. So, to me, it's clear because of the 50 hours and they hadn't crashed yet that they didn't have a regimented test program. No formal risk assessment and mitigation plan. And I make a special note here at the end. Innovation is risky. In fact, we never should say, I'm going to innovate, or you're stopping me from innovating, or you don't know how to innovate. It just should take that out of our lexicon and say, I want to take a risk. My plan here is to take risks in an incremental, cautious fashion so that I can get to a point where I have better performance. And then when I get there, I say, see, I innovated. But really, when going into it, all you're doing is taking a risk. Anytime you think you're going to innovate, do something new and different, the risk alarm should be going off full blast, because that's exactly what you're doing. And there was a boatload of innovation on this design. Couldn't help it. At the time they designed the Flair, I was flying my first wing, the Swift was flying, that was about it, of real life flying examples. So pretty much everything they did on the Flair was an innovation. That was nothing but risk from winglet to winglet. Okay, so no formal risk assessment and mitigation program. I believe they did not do this because I came to the conclusion they didn't have a regimented test plan. Because a regimented test plan is married to this guy. And it's where you identify potential risks, assess them in terms of probability of occurrence and severity of the results if it does occur, and you map these out and you track them, and some are red, some are yellow, some are green, and if you have red ones, you better stop and figure out something different. You got yellow risks, well then you're going to proceed with caution incrementally, and you're going to manage those risks as best you can. However, that said, this area of work, this risk assessment, is esoteric at best. I was on a program at Lockheed. I'll tell you what it was the THAAD program. As we were developing that missile, we had a risk list of about 250 items. We could have had a lot more, but that was the initial reasonable risk list. And then a bunch of engineers, dozens, worked really hard to whittle it down to the 12 key risks. And then we put specific mitigation plans in place for each one of those risks. And then when we went out to fly the missile, well, we had problems right away. And only one of the risk items on the list actually came to be. The other ones never happened. But there's a whole bunch of stuff that did happen that went bad, caused missiles to crash, like I think it was all 13 of the first batch. It was horrible, systemic problems end to end. And those risks hadn't been identified, never got on a list. Why? A bunch of stupid engineers? No, you got PhDs and master's degrees left and right, mechanical, aero, great management. A company that's been designing and building missiles for 40 years, and still there's all this stuff happening that we hadn't identified as risks. And that comes to something I'm going to talk about later, and that's the Dunning-Kruger effect. And that's what happened at Lockheed. So this area of risk assessment and mitigation, iffy at best. That's why we still move forward in small baby steps on the test program, because we don't know what risks we might run into that we hadn't thought of before. And I could find no verifiable collection of test data. And I'm working on a very minimum level on that. Out of all the pictures I've ever seen of the Flair, there's not one picture where there's tufts on the wing, tufts of yarn on the wing, that they're looking at the flow conditions on the wing. And I find that shocking. I'm sure there's lots of photos out there I haven't seen, of course. Hold on one second here. And those photos with the tufts on there might exist. If they do and you have them, post them. But at a minimum, you're going to tuft your wing even before your first hop. Myself, I put tufts on my wing. I go stand in the wind. I don't even leave the ground. I don't even attempt to fly. And we look at what the tufts are doing. And we acknowledge, okay, it's not the right Reynolds number range, but it tells me something. If I have separated flow, I'm going to see it. And you'd be hard-pressed right now to find a picture or a movie of my wing after we started testing that doesn't have tufts on it. They've been there the whole time. I keep putting new ones on. So if all you find of my wing is pictures of it with tufts on it, how come I find all these pictures of the Flair flying and sitting on the ground? No tufts. Where are they? So I have to conclude that they weren't collecting test data, because that'd be the minimum test data that you would collect. Like, before I go out here the next time, I want to have my full AHARS system in there, and I'm going to have pitch rates and yaw rates and roll rates and angle of attack information and airspeed, because these days that system is now affordable for a project like this. You can do it for a few $100. And I'll be posting that data on YouTube when it comes in. It'll be nice to have. But you have to have a professional, well-established test program to tell you, oh, I need to collect this data here and I need to collect that data there. Now, it could very well be that they had other data and just it's posted somewhere, recorded somewhere. I know there's a person out there who's still around who has a lot of that, who might have a lot of information like that, and they're not talking. And the word is they will not talk to the general public or people about it like me who do YouTube, because in the past they've been misquoted, and they said, I'm not going to do that again. Which causes much harm to what we're trying to do when we do accident analysis. This is an accident analysis so we can learn what not to do in the future or what to do in the future. So the fact that that person has chosen not to speak on the subject is a loss to the entire aviation community. It's a darn shame. And I believe they have a moral obligation to come forward with the information that they have, that they're currently not sharing. So, no verifiable collection of test data. So, no numbers to look at in terms of hard numbers that actually occurred in flight. So I've had to make estimates on that, and you'll see that over on the technical side of the video. So here's a big one: lack of good teamwork. And by teamwork, I'm talking about the team that was developing the aircraft and the government entity involved, the DHV. Now, and it's very clear in the writings that there was, and the people I've talked to, that there was a conflict between the DHV and the development team. And it wasn't a fault of one side or the other. It's a fault of both sides, not understanding what their obligations are and what they're doing. It was the DHV saw their position, their job. The DHV saw their job as to say no or yes. That was their job. That's what they were assigned to do. Assess this aircraft, and if it's safe to fly, give it a certification. They certify or they don't certify. So the DHV did test the Flair. They did vehicle testing and came back with a no. And that was before the crash occurred. The DHV says stop flying that aircraft. What they didn't say was, they didn't come back and say, I think there might be an issue in this area, and let's sit down together and do more analysis to see if we can figure out whether it's a serious risk or not. And the reason they didn't do that is because that wasn't their job. That's not what the government had assigned them to do. That's not a yes or no answer in terms of being safe to fly. That is becoming a member of the development team to help them develop the aircraft. And they weren't assigned to be helpful in that way or to do that work. Their job was a gate to say yes or no. And the design team is wanting to be very innovating. They love to innovate, from what I heard. Cool stuff. New, different, better, higher, faster, further. And anytime you have an entity whose job it is to say no, and you have an entity that wants to move forward, when they hear no, what they hear is, they're just trying to prevent me from innovating. And I'd say, you're probably right, because innovation is risk. And they're probably trying to prevent you from taking too much risk. And yes, that will stifle innovation. But if you sit down and do more calculations and listen to that other person, be humble, listen to what they have to say, ask them questions, try to sort it all out, work together as a team. But they were in conflict. And when you're in conflict, you can't work as a team. And if any of you are out there that are listening and are married, you know exactly what I'm talking about. You get in conflict with your spouse, you can't solve any problems. You have to work together as a team. They were not working as a team. And there's a variety of reasons for that, and one of them is the classic one. You got one group that wants to innovate, you got another group that just wants to be the gate and say yes or no. They were working opposed to each other. Actually, what would have helped is if the government had assigned the DHV the task of identify where these various projects could use help and go help them. But that's not what the DHV was set up to do. I had one person tell me the DHV just wanted to stop all the developers. I'm sure that wasn't their only goal. Okay, so teamwork. Teamwork requires excellent management. And it's management that understands all of the human factors and understands both sides, government side, developer side, and needs to understand the people and how they mesh together. And that management task, I've done it many, many times, is the hardest thing in the world. Because you have all these different personalities, they're motivated by different factors, and to try to manage them as a group, to get to a goal, and stroke everybody's ego, it's hard. It's really, really hard. And they keep moving on you, and they go over here and they go over there. So, oh, it's a nightmare. Anyway, so teamwork. How do you do it? I would say what this project probably lacked in a formal sense was what we call systems integration, a systems integrator. Somebody that is knowledgeable of all of the technical topics and is also a good people person and can bring all of those pieces together and blend them together into one. On my project, I avoid that by not having all of those other people. I am the designer. I am the builder. I am the test pilot. All in one. It's very easy to integrate all of those aspects together because it's just one person. Some people might say I have a split personality, but no, it's just me. And I don't have to try to go over to somebody else and get the structural analysis and blend it in with the arrow, because I do that concurrently as I go through the design because it's just me. I still have to be open to other people coming in and saying, I think you made a mistake there. Always have to be ready for that. So, teamwork. Marketing goals. It is clear in what I read that there were marketing plans for this aircraft. That makes it very clear that they're selling. Okay, so the wing area is a little small. Well, the wing area is a little small. We designed it this way, so it'll go fast. We want to be able to go long distances. But it's foot launch. Yes, it is. Well, how are you going to slow up? Well, we have this wide speed range available because of this special flap that we designed. And as a matter of fact, we have a naming contest for that flap. Naming contest. What do you get for if you have the winning name? You get shares in the company. If that's not marketing, I don't know what is. Let me put up here an example of an aircraft that was designed with marketing in mind. And they were big time marketing. They had a guy on the team who did marketing exclusively. And when I first saw that aircraft fly on YouTube, I went, oh, it's got problems. Because I saw it doing stuff that I know that flying wings do when you make certain choices that are not necessarily the best choices. And they were pushing hard. They were on a schedule to get to Oshkosh because they wanted to market it at Oshkosh. And I wrote them a series of notes via YouTube about, hey, I think you might have a problem there. Here's my qualifications. I'm not just blowing this out of the side of my head. Here's the problems that you might be having and why you're having them. And then I pointed out the aircraft may not be safe to fly as is. And I see you trying to make aerodynamic fixes on it because you see these other components being modified, aerodynamic modifications. And no answer back. And through a third party, I finally found out that they had read those messages. They went and looked at some of my videos, half of them. I had a whole series on how to prevent stall spin, and they watched half of it. And went back to this other person and said, he doesn't know what he's talking about. The classic person comes along just trying to help. But in trying to help, I have to say, no, don't do this. And they're offended because I don't know anything about their design. How could I know anything about their design by watching a video of it? Well, I've worked on flying wings for 40 some odd years. I've had dozens of designs and I've seen that before. So, bottom line, they never got to Oshkosh, never made it there. Don't know why. And as far as I know, they haven't flown since then. Why? Don't know. They went silent, they went dark. Their website's still up. You can still sign up for their electronic newsletter, but I haven't heard anything about it flying. I haven't heard anything about it crashing. What happened? Well, maybe what happened is they were a little too focused on marketing and not focused enough on the engineering side of it. And they didn't have an open mind to hear messages coming in that saying, maybe you've made a boo-boo. And well intended, but they're not going to listen to it. And that is a huge human factor that will cause all kinds of problems on projects like this. And that happened with the Flair. The DHV went back to the team and said, stop flying. Literally. And what they do? They continued flying. And we know what the result was. Very hard to hear those outside messages coming in. I can't shame them or fault them. It's a human foible. It happens to all of us. And as I said, it's happened to me. And it takes a little while to have your adrenaline settle down and sit down and think about it analytically. It's not personal, it's just engineering. Okay, so marketing goals may have clouded sound engineering judgment. If you got money out the door to develop a design, which they did in this case, how much money, I don't know, but money was out the door, and you think that you're going to build these to sell them, that's a motivation that will cause poor choices to be made many times. So now we get down here to the Dunning-Kruger effect. If you don't know what that is, I invite you to look it up on Wikipedia. It's a pretty good write-up. And I don't mean this in any shameful or derogatory manner. I'm talking about this from a strict, we all have this issue. And basically the Dunning-Kruger effect says you don't know what you don't know. In the aerospace industry, we call those the unknown unknowns. And on the THAAD program, we had a lot of them because the missiles fell out of the sky. We went, oh, we never thought of that. Oh yeah, that could happen. In fact, it did happen. We didn't know what we didn't know. And it's impossible to know what you don't know. And if you're not trained in a particular field, it's even more so because you don't have any of the information that's in your head that says, this is a really difficult topic or subject or area of study. It takes decades to really learn this stuff. And therefore you get overconfident. You go, oh, I have these equations, I have this computer code, I can design this aircraft, I can do this. And then I certainly was that way when I started. My first flying wing design was when I was 19 years old. That didn't fly. But 40 some odd years later, I sit there and go, wow. The information that I've gathered over the years in my own brain about how this stuff works is huge. So that's what makes me sit down and say, I have no idea what I'm doing. Therefore, I better proceed with caution. So the Dunning-Kruger effect will cause people to move forward without sufficient caution. And how you deal with that in the aerospace industry is you go right back up here to formal risk assessment and management. Because that will help you get past the point of this, we didn't know that stuff. Partially. And then the incremental small test program to expand the flight envelope so that if you do encounter a landmine out there, well, A, it might not do too much damage, or you might be able to quickly step around it. And then you can add that to the list of things you know. And then that becomes a known unknown. Oh yes, I know this can be a problem, but I don't know how it goes bad. So I'm going to have to do some more work to figure out what actually causes this to go bad. So all of this is a very formal air vehicle development methodology that probably was not followed with the Flair because it's a small informal group. Not all of them are professionally trained, and somebody's forking over money and they don't have infinitely deep pockets. They don't have $1 billion. So that's what happens. Somebody move forward too rapidly or to the wrong place just because you don't realize there's landmines out there in that area. So Dunning-Kruger effect, and we have to go into every single one of these projects that we do, understanding there's a whole bunch of stuff we don't know, especially with flying wings. So if you're out there doing a flying wing design, stop and think, ask other people their opinion, lots of them, especially if they're well-qualified engineers, and proceed with great caution. As far as I know, this endeavor, the most dangerous thing going, development of aircraft, extremely dangerous. And if you cut corners or you don't know what you're doing, somebody dies. So if you, before we go on to the other part, if you haven't already been there, get those write-ups on my Patreon site. They're free. Access to the Patreon site for this stuff is free because I want this information disseminated as widely as possible. And while you're there, you can actually sign up as a Patreon member for free, no charge. You won't have access to all of the stuff that's there, but there's some stuff that's there for the public and free members, and I hope you enjoy that material. So please, go on over to Patreon. Link is in the description of this video. Just click on the link, go over there, sign up as a free member, and take a look at this stuff that I'm posting from the Flair project. So there, I've covered human factors. I hope I haven't offended anybody too greatly on it. And now that I've talked through it, I feel better that I've gotten that out of my system, but I'm also a little bit sad again because I see a group of people that ended up with a disaster when it could have been, probably could have been avoided if they had done these other things. And the fact that it did crash and it ended up this way is most likely because this stuff wasn't done. But I'll end by saying I could be entirely wrong about this. And there might have been, all this stuff could have been done, and people just ignored the results. That happens too. So that's why I finish every single one of my videos with, please fly safe and bye for now.